Visualizing the distribution of data is an important tool for statistical communication. Distributions are useful because they allow reasoning about a variable in terms of densities and probabilities. The histogram is a simple tool that is used to visualize the distribution of quantitative data. It works by sorting data into bins, counting the occurrences within each bin, and representing these counts as a vertical bar in a plot. The differences in counts between bins explains what values might be more or less likely than others. But why choose the histogram? The histogram works for continuous data. It works for some discrete data. It can be computed quickly, needing to loop over the data just a single time, and it is familiar to a wide range of audiences. Here's an example of the discrete case that visualizes 50 samples from a binomial distribution. In this animation, outcomes are stacked on top of each other, just like how a histogram counts occurrences per bin. As more samples are gathered, a distributional shape starts to emerge. This binomial distribution is symmetric with a mean of 5, so it is expected that values further from the mean have fewer counts than values closer to it. When the data is continuous, counts cannot be calculated based on exact outcomes. Values falling within fixed width intervals are counted instead. In this example, bins have a width of 1/2. The histogram is almost completely defined by the design of these intervals. Here is the interval that describes the mth bin. A is the smallest value considered by the histogram and is equal to the lower bound of the first bin. H controls how wide to make these intervals. The interval is closed only from the lower endpoint. This prevents overlapping bins that might result in an observation being counted twice. These values can be used to calculate what bin an observation belongs to. The observation xi falling within the mth bin can be written as an inequality. The value m-1 is simply the bin index of this observation. Solving for this value gives the following result. The floor function is applied because m-1 is the greatest integer less than or equal to x minus a over h. One way to choose the number of bins is by Sturge's rule. Dividing k by the range of the data returns a value for the bin width. Alternatively, there is the Friedmann-Diaconis rule. This value is found by adjusting the bin width based on some optimization criteria, such that the histogram matches a theoretical distribution of interest. However, these rules make some assumptions about the data, such as it being normal or symmetric. In practice, a trial and error approach to choosing a bin width, using these mathematical rules as a guide, is useful. For example, if these rules take into account scale and sample size of the data, maybe we should too. Here is a rule of thumb for choosing a bin width, assuming that the scale of the data is fairly constant between sample sizes. Using a small bin width for small sample sizes is undesirable. Many bins will be empty or contain just a single observation. The histogram will be overly sensitive to the exact data sample it describes. If lots of data is available, but a large bin width is chosen, the histogram will not be flexible enough. This results in a biased histogram that misses the important details in a given data sample. For small sample sizes, a compromise should be made for a large bin width. This provides a summary of the data that abstracts away each individual observation. The ideal case is using a small bin width when the sample size is large. This permits a visualization of the data distribution at a high resolution. The compromise between larger and smaller bin widths exemplifies the bias variance trade-off, a key concept in machine learning. In this animation, a histogram is updated 10 samples at a time. For each update, the bin width is recalculated according to the Friedmann-Diaconis rule. As the sample size grows, so does the number of bins. This produces an accurate reconstruction of the two-part normal mixture filled in white, used to generate the data. Here's an example putting this all together to construct a histogram from data. First, the bin index for each observation is calculated. These data are 10 samples from a uniform distribution. So A, the minimum value, is chosen to be 0, and the bin width h is chosen to be 0.25. This gives a total number of 4 bins. The number of observations belonging to the same bin index are counted by the bar graph. The histogram is completed by plotting the final count for each bin over the midpoint of their respective interval. This video aimed to provide an introduction to the histogram. In summary, it covered what a histogram is, a tool for visualizing the distribution of quantitative data, how to choose a bin width and its connection to the bias-variance trade-off, and how to construct a histogram step by step using a simple example dataset. There were, of course, things that were left out. Instead of counts on the y-axis, alternative scales such as relative frequency or relative frequency density are common. These are particularly useful when comparing distributions is a priority. Histograms can be constructed using variable bin widths. The idea here is to use smaller bins where lots of data is available, and wider ones where it is not. The histogram is not the only tool for visualizing the distribution of data. For example, if smooth density estimation is important, then kernel density estimation might be a more useful tool.